Hello and welcome to G Fun Facts Online. Today, we are going to dismantle the way you perceive time. We live our lives governed by the clock, swimming in the invisible river of time, yet most of us rarely stop to ask how we actually measure it. For the last 60 years, our entire modern civilization, from the synchronization of the internet to the GPS on your phone, has rested on the shoulders of the atomic clock. We defined the second based on the behavior of electrons orbiting a cesium atom. We thought we had reached the pinnacle of precision. We were wrong. A new revolution is currently underway, one that makes the atomic clock look like a crude sundial in comparison. As of late 2024 and 2025, scientists have successfully prototyped a device that operates not on the electron, but on the nucleus of the atom itself. We are entering the era of the nuclear clock. In this episode, we are going to dive deep into the mechanics, the physics, and the mind-bending applications of this technology, which promises to be so accurate that it wouldn't lose a single second over the entire age of the universe. To understand why this is such a massive leap, we first have to understand the fundamental limit of our current technology. All clocks, whether it is a grandfather clock or a quartz watch, work on the principle of resonance. You need something that ticks at a steady frequency. In a standard atomic clock, that ticker is an electron. When you hit a cesium electron, with the right frequency of microwaves, it jumps between energy states. That jump is our tuning fork. But there is a flaw in this design. Electrons are lightweight particles that live on the outskirts of the atom. They are exposed to the world. A stray magnetic field, a slight temperature fluctuation, or even a collision with a gas molecule can disturb the electron and shift its frequency. To make atomic clocks accurate, we have to build room-sized vacuum chambers and use magnetic shields to protect these fragile electrons. Basically, the electron is like a pendulum swinging in the wind. To get better time, we need a pendulum that is heavier, stiffer, and protected behind an impregnable wall. That is exactly what the nuclear clock provides. We are moving from the electron cloud down into the nucleus. The nucleus is held together by the strong nuclear force, which is 137 times stronger than the electromagnetic force holding the electrons. The protons and neutrons inside are packed so tightly that they oscillate at incredible frequencies, usually in the X-ray or gamma ray range. Because the nucleus is tiny, about 100,000 times smaller than the atom itself, it is naturally shielded by the electron cloud surrounding it. It is immune to the noise of the outside world. If you could build a clock based on the nucleus, it would be solid state, robust, and insanely accurate. For 50 years, this was just a theory. The problem was energy. To tickle a nucleus and make it tick, you usually need massive amounts of energy, like X-rays. We simply do not have lasers that can produce coherent X-rays to start the clock. The nuclear clock seemed impossible to build, until we found the anomaly. Nature gave us exactly one loophole, and it is found in the isotope thorium-229. Thorium is a heavy, radioactive metal, but this specific isotope has a freakish property. In 1976, physicists noticed that thorium-229 has an excited state that is tantalizingly close to its ground state. The energy required to make the jump is only about 8.35 electron volts. To put that in perspective, most nuclear transitions require millions of electron volts. 8.35 is not an X-ray, it is in the range of vacuum ultraviolet light. This is a cosmic accident. The forces inside the thorium nucleus just happen to cancel each other out in a way that leaves a key under the doormat for us. It is the only nuclear transition in the entire universe that we can reach with lasers. But even knowing this, it took 40 years to find the exact frequency. It was like trying to tune a radio to a station when you don't know the number and the dial spans the universe. The breakthrough finally came between 2024 and 2025. This is the cutting edge of science happening right now. In early 2024, a team led by researchers in Vienna finally pinpointed the frequency using a crystal of calcium fluoride doped with thorium-229. They blasted it with a specialized laser and saw the nucleus glow. They found the station at approximately 2,020 terahertz. Then, in September 2024, the team at Gila in Boulder, Colorado, led by the physicist Jun Ye, built the first fully functioning prototype. They managed to link the frantic ticking of the thorium nucleus to a standard atomic clock using a Nobel Prize-winning technology called a frequency comb. This device acts like a gearbox, translating the petahertz speeds of the nucleus down to something we can count electronically. They achieved a measurement with 12 digits of precision. This proved that the impossible clock was real. But what makes this technology truly revolutionary is the design. Unlike atomic clocks that require trapping individual atoms in a vacuum, the nuclear clock can be solid state. Because the nucleus is so well shielded, you can embed billions of thorium atoms into a solid crystal lattice about the size of a grain of rice. The crystal protects them. This means we aren't just building better clocks for labs. we are paving the way for chip-sized sensors that are portable and robust. So how does this machine actually work under the hood? It starts with a crystal core, specifically calcium fluoride, which is transparent to vacuum ultraviolet light. This is critical because VUV light is absorbed by air, so the whole thing sits in a vacuum. To drive the clock, scientists use a process called high harmonic generation. They take a powerful infrared laser and blast a gas, like xenon, ripping electrons away and slamming them back to create bursts of high-energy photons. This generates the precise 148 nanometer light needed to hit the thorium. When that laser hits the nucleus, a neutron inside flips its orbit. The nucleus expands by a femtometer, a distance smaller than an atom, and changes shape. That shapeshift is the tick. By locking the laser to this transition, we get a time signal that is orders of magnitude purer than anything we have seen before. Now, why does this matter? Why do we need a clock this accurate? It isn't just about knowing the time. This device is a telescope for the fundamental laws of physics. The nuclear clock is estimated to be 10,000 to 100,000 times more sensitive to changes in the fundamental constants of nature than atomic clocks. Specifically, it can test the fine structure constant, labeled alpha, which dictates the strength of the electromagnetic force. Some theories suggest that these constants aren't actually constant, but change slowly over time or interact with dark matter. If a wave of dark matter passes through the Earth, it might cause the constants to wobble slightly. A standard clock wouldn't see it, but a nuclear clock would speed up or slow down. A network of these clocks could act as a dark matter observatory, listening for the invisible hum of the universe. On a more practical level, this technology will transform how we understand our own planet through a field called relativistic geodesy. Einstein taught us that time moves slower closer to massive objects due to gravity. Current clocks can detect time differences at height changes of about 1 centimeter. A nuclear clock could detect time dilation caused by millimeter or even sub-millimeter changes in height. This turns the clock into the ultimate gravity sensor. We could detect magma moving underground before a volcano erupts. We could see tectonic plates shifting before an earthquake happens. We could even find new oil or mineral deposits, just by sensing the tiny changes in gravitational density they create. Furthermore, this leads to the next generation of navigation. Currently, GPS relies on satellite atomic clocks, giving us accuracy within meters. A nuclear-based system could provide millimeter-level accuracy anywhere on Earth. More importantly, it allows for autonomous deep space travel. A spacecraft going to Mars or Europa cannot rely on GPS signals from Earth because the delay is too long. With a nuclear clock on board, a ship could navigate by the stars and pulsars with perfect timing, landing itself autonomously on an alien world. We are currently at the Wright Flyer stage of this technology. The prototypes exist, but they are complex. The road ahead involves developing better lasers and refining the crystal growth to ensure perfect purity. By the late 2020s, we expect to surpass the best atomic clocks. By the 2030s, we could see miniaturized chip-scale nuclear frequency references. The history of timekeeping is the history of civilization. Every time we improve the measurement of time, we change society. The sundial gave us the calendar. The pendulum gave us the schedule. The atomic clock gave us the digital age. The nuclear clock represents the final frontier. We are locking our time to the dense, quiet, unshakable heartbeat of the atomic nucleus. We are building a ruler that will not bend, a device that will outlast the stars. In the silence of a vacuum chamber, inside a tiny crystal, a thorium nucleus shudders. In that tiny movement lies the future of navigation, the map of the invisible universe, and the next leap for humanity. Thanks for listening to G Fun Facts Online.